Then I'm going to share screen. Okay, so everybody can see the file now, right? Chapter 19. Okay, this is page 11. Oh, here we go. So before we start this, is there any questions on the previous part of chapter 19? I guess not. Okay, anyway, so the concept of conjugate acids and bases is pretty simple. So here's an acid. That's acetic acid. I can tell it's an acid because of the hydrogen in front. Then here's water. Water we have to think of as being able to act as an acid or a base. And so I can see that this hydrogen is going to go from the acid to the water. When I know that, I can figure out what's going to be on the other side of the equation. So this would be the acetate ion, and this would be the hydronium ion. So that's not new. But if we look at going reverse, if now these are going to react and go back to form the original reactants, then which one is going to be the acid, which one is going to be the base, because that's also an acid-base reaction. So I can see that this one is the acid, and this one is the base. I'm just looking to see where the hydrogen ion goes. So because this is on the product side, we call it the conjugate base and the conjugate acid. So here we see water acting as a base, right? If you put a base into water, then we make water act as an acid. So I see the hydrogen go from water to the ammonia. So it makes water the acid, ammonia the base. Now if I have to figure out what the products are, it's simply that H plus goes from here to here. So I get the products. So what if these were going to go back and form the original reactants? Which one is the acid? Well, certainly not this one. So this one is the acid. To get backwards, to get those reactants, I would have to have the H plus go from here to the hydroxide, making this the conjugate acid and this the conjugate base. So now we can look at these as base acid-base pairs. So here's the base, here's its conjugate acid. Here's the acid, here's its conjugate base. Same with up here. So what do you do to get the base into its conjugate acid? All you do is you add a H plus. What do you do to get the acid into its conjugate base? You simply take off H plus. So here's some examples. Here's sulfuric acid. There's two acidic hydrogens there, but we take off only one. Here's hydrogen sulfate. We take off only one. Somebody asks you, what is the conjugate base for the sulfate ion? You can tell them that what a stupid question that is, or you can explain to them, well, there's no hydrogen to take off. Here's the hydronium ion. If you take a hydrogen off, you get the conjugate base as water. Water gives you hydroxide. Hydroxide gives you oxide, which is a strong base, by the way. But there is none for the oxide ion. Here's the ammonium ion. The conjugate base is simply ammonia. Here's ammonia. The conjugate base is the amide ion. Now here's something that's kind of interesting. Because I teach organic chemistry and have done some synthesis in my career, I know how to make the amide ion. This is a base, and some people say, well, you can't make a conjugate base from a base? And the answer is yes, you can. You just have to know how to do it. So here again, could I take off an H plus? Yes, I could. It may not even be likely, but you could do it. So your job is simply to take it off if it's there. You can't be expected to know everything. If we look at getting the conjugate acid, we simply add an H plus. So here's sulfate, we get hydrogen sulfate. Here's hydrogen sulfate, we get sulfuric acid. Here's sulfuric acid. Could we get this? The answer is not likely, but could we do it? Yes, we could. We simply have to have an acid that is stronger than sulfuric acid. If you go back and look at the pKa's or the Ka's of that list of strong acids, you will see that there are acids that are stronger than sulfuric acid. So I could do this. So here is oxide going to hydroxide, hydroxide going into water, water going into hydronium ion. So anyway, just to give you an idea. So here's a typical problem that would be on the final. Give the equation for a weak acid, such as H2S, dissolving in water. So this is one of the things I've been emphasizing. Students simply, somehow, they don't know how to do it. All you do is you take it and you put it in a water. And now, if you consider that water is neither an acid nor a base, if you consider that they're extremely weak, either one, this has to be the acid. So the H plus goes from here to the water. So I get hydrogen sulfide and hydronium ion. So since the hydrogen went from here to here, that's the acid, that's the base. Now if I had to go from here back to the other direction, which one is going to act as the acid? Well, this is going to be the acid. So I can restore what I had over here. So that's the conjugate acid and the conjugate base. So notice that I put a double-sided arrow here because this is not on your list of strong acids. In the next example, I use perchloric acid. This is on your list of strong acids, so that's why there's a one-directional arrow there. So as soon as perchloric acid touches water, it's gone. It's 100% in this form now. Okay. Then again, hydroxides give us a problem. So if I tried to do this with, say, magnesium hydroxide, okay, so I go forth and I put the acid in here and I get magnesium ion, I get the 2 hydroxide ions. It's like, well, wait a minute. If this and this are the same on both sides, they cancel out. So I don't really have a way to do the acid and the base. It doesn't work. Okay? So it's just a matter of semantics. So this next one, give the equilibrium constant for magnesium hydroxide in water. So magnesium hydroxide is only partially soluble in water. So here's the reaction. Notice that I don't have water here because it already has hydroxide in it. And I put the solid form there. So if it's not very soluble in water, I'm going to get a saturated solution. Nevertheless, I take the products, put them over their reactants. Notice that this times this is now squared, right? And I'm leaving out pure liquids and pure solids. So I'm leaving out the solid magnesium hydroxide. So the equilibrium constant can be called the Kb because it's a base. It can also be called the Ksp, which stands for the solubility product. So in other words, if I made a solution by taking solid magnesium hydroxide, dissolving it as much as I could into water, I'm going to get this amount that's dissolved, and this amount would not be dissolved. But this amount, we leave it out because it could be a speck, it could be like a pound. So that's why it's called the solubility product. So the anion and cation is multiplied. So here's a diagram for that. So I add magnesium hydroxide. Some of it will dissolve and I'll get a saturated solution. And the amount down here doesn't really matter. That's why we leave it out in the equation up here, Ksp. So any questions about that? Yeah. There must be some faculty that gave up asking questions. So here's another one that's very similar to that. So iron 3 hydroxide in water is not very soluble because hydroxides are not very soluble. So here would be the reaction for it. So here would be the base, here would be the base, right? There is no acid. So to get the equilibrium constant, it's products over reactants. And I combine the like terms here, so that's why this is cubed. And then this is a solid, so it's left out. So here's what the Ksp would look like. So this is kind of interesting because if I wanted to know how much iron 3 hydroxide will dissolve, in other words, if I wanted to know the concentration of a saturated solution, all I would have to do is go look online and find out the number for this. It's a constant, and I'll be able to figure that out directly. So the next part is kind of difficult because of the way textbooks treat this. And so I'm trying to make it more simplified. So if HA is a strong acid, that means it really wants to get rid of its H+. So if it does get rid of its H+, what is the likelihood that the A- will then take the hydrogen back again? The answer is not very great. So what that means is that the conjugate base of a strong acid is going to be a weak base. So same thing goes with a conjugate acid. If you have a strong base, the conjugate acid is going to be a weak acid. So a couple things to remember. Most acids and bases are not weak, they're not strong, they're moderate. Water is both very weak acid and a very weak base. And so if hydronium ion is a strong acid, that means that water is a weak base. If hydroxide is a strong base, that means that water has to be a weak acid. So just to summarize that, strong acid has a weak conjugate base. A strong base has a weak conjugate acid. Moderate gives you moderate, and weak gives you strong. Okay? And again, we only have to worry about the 7 strong acids to really deal with this. And what about the strong bases? Those are just the hydroxides. Which I probably should add that right here. Okay, so Here's some examples. Give the equation for H2S and water. Label the acid base, conjugate base, and label each as strong, weak, or moderate. So this is not on my list of strong acids, so I would treat it, some books would say a weak acid, but no, it's not really weak, it's in the category of being moderate. Most of them are. That would be your assumption. Then water, we know, is very weak. So when my acid gives the hydrogen ion to the base, these are the products I get. So to get back to the original reactants, hydrogen will have to go from here to here. Here's my conjugate acid, here's my conjugate base. Now this is a strong conjugate acid. And what is its base? Very weak. And this was on your list of strong acids, wasn't it? So then if you go to the acid, its conjugate base, they're both going to be moderate. So here's another one. Here's a strong acid that's on your list of strong acid. Its conjugate base would therefore be weak. Okay. And then here's a very weak base. Its conjugate acid would be strong. So let's see. Here's a weak one. So here's a moderately strong base. Its conjugate acid would be moderately strong acid. Here's a weak acid, so its conjugate base would be strong. So what about sodium hydroxide in water? Okay, I left out the sodium ion, and what we see is there's really no reaction here. You're simply adding hydroxide to the water, and it affects the pH directly. So understanding this part right here is really key to being able to understand the hydrolysis of water by salts. So the addition of some salts to water will change the pH, even if there's no acidic hydrogens or no hydroxides in the formula. So here's what I mean by that. If I add sulfate, I'm going to raise the pH of water. Here's why. Because it hydrolyzes water and creates the hydroxide. So here's the base, making water act as the acid. Here would be my conjugate acid and my conjugate base. But because I form a little bit of hydroxide, you know what that does? That raises the pH. It makes it alkaline. So here's the Kb. The Kb is a very, very small number. So that means every trillion sulfates will produce only one hydroxide. But as you'll see, sulfate is one of the major things that makes the ocean alkaline and not acidic. Fluoride. So here's a moderately strong base. I put it in water and I hydrolyze the water. I form a little bit of hydrofluoric acid, and when I do that, I make some hydroxide. So here's the equilibrium constant. The Kb for fluoride is a very small number, but it's enough to raise the pH a little bit because you are creating some hydroxide. On the other hand, sodium chloride does not affect the pH. So if I take sodium chloride and put it into water, the sodium doesn't do anything because that doesn't form. Okay. What about the chloride? Well, I put the chloride in here, and its conjugate acid is going to be HCl, which is a strong acid. And the conjugate base of water is going to be a strong base. So these things are both extremely strong. You're not going to go form that. Not going to happen. It's going to go this way. So for that reason, sodium chloride does not change the pH of water. It does not hydrolyze water. Sodium phosphate will raise the pH of water because phosphate causes hydrolysis of water. So here's the base, making water act as an acid. You will form some of this because it's not very strong. If you make any of this at all, then you're going to raise the pH. So there's a couple more there. I put it in a red box because I'm not going to put that on an exam or anything, but you at least need to know about hydrolysis of water by salts. So now we can look at something more practical here. So the pH of the ocean ranges between 7.5 to 8.5, depending upon different aspects. But that's alkaline. That's basic. There's so much CO2 in the water that the CO2 should make water acidic. This is the reason why rainwater is acidic. This is the reason if I take tap water and say it's pH 7 and I exhale through a straw into it, the pH could easily go down to like 6. CO2 forms carbonic acid, which is an acid. CO2 dissolved in water forms carbonic acid, it produces this. So the two major bases that hydrolyze water and make the ocean basic, it's not sodium chloride, it's sulfate and fluoride. So here's sea salts over here. Seawater is only about 3.5% salt, the rest of it is water. If you take that and analyze it, mostly it's sodium chloride, which will not affect the pH. But look at sulfate. It's 7.7% of all the salts in the ocean. That's a very high amount. By the way, where do you think that sulfate came from? I would say mostly volcanic action. Volcanic action produces sulfur dioxide, sulfur trioxide. Those react with water to form sulfurous acid and sulfuric acids. Those wash out of the water down through the rain and into the water. That's where we get our sulfate from. So then we see that calcium is a little bit, potassium, magnesium. You don't see fluoride there, do you? Fluoride is a very small amount, but yet it is enough to actually influence the pH of the ocean. So, questions so far? And let's look at water again. So you've seen water act as an acid, water act as a base. Would you be surprised to see that water can react with water to form hydronium ion and the hydroxide ion? And so what they found is that at 1 atmosphere and 25 degrees, the concentration of both of these, hydroxide and hydronium ion, is 1 × 10 to the -7th moles per liter. So why is water neutral then? Because that's not 0 and that's not 0. Water is neutral because the amount of hydronium ion is equal to the amount of hydroxide ion. And then where do we get the number pH 7 for pure water? Well, if I take the negative log of 1 × 10 to the -7th, I get 7. Okay. So what does it mean if an aqueous solution is acidic? that means that there's more hydronium ion than there is hydroxide ion. So let's do an example of that. So say neutral water, pH 7, so we got 1 times 10 to the minus 7. What would be a more concentrated value for that? Maybe 1 times 10 to the minus 6, 10 times more concentrated of hydronium ion. That would give us pH 6. So therefore we know that if the solution is less than pH 7, it's slightly acidic. If it's greater than 7, then it's slightly basic or alkaline. So your blood, for example, has a pH of about 7.4. So is it neutral? The answer is no. It's slightly basic or slightly alkaline. So now we're going to expand our use of the negative log concept. And we already learned how to get the pKa from the Ka. We simply take the negative log, right? So now we're going to do the same thing with the hydronium ion. The negative log of the hydronium ion is the pH. So how do we do this? Well, it depends upon your calculator. So here's one logic of a calculator. Here is another one. And you will always be able to figure out if the calculator keystrokes are working, because you should know that 10 to the minus 7 should give you a pH of 7. So another thing I could point out is that is a property of logarithms. Notice that the negative log is the same thing as the log of the inverse of whatever you take the negative log of. See how that works? So another way to do the log is you take the hydronium ion, flip it over by doing the inverse function, and then take the logarithm of that. That's the same thing as taking the log and then changing the sign. So hopefully your calculators will do this quite easily for you. Calculate the pH of a solution if the hydronium ion is 1 times 10 to the minus 9. Well, you should get a pH of 9. And notice about significant figures. This number right here has 3 significant figures. This number right here in terms of pH has 3 significant figures. These are where the significant figures come from. That minus 10 to the minus 9 is that 9 right there. So this simply refers to the closest power of 10. And this gives you the number of significant figures right here. So I gave a couple. You just have to make sure you got the keystrokes correct on your calculator. So here's another one. So besides converting hydroxide into pH, we can take the hydroxide and turn it into the POH. It's the same exact mathematics. So calculate the POH of a solution with the hydroxide ion concentration of this. So I can see that this is going to be close to a POH of 5. If this were a 1, right? 1 times 10 to the minus 5, I would get 5. But because this is not a 1, it factors into being this shy of that. Okay. So now we know how to take the Ka, turn it into the pKa. We know how to take the hydronium ion, turn it into the pH. We know how to take the hydroxide ion, turn it into the POH. But you know what? We can also reverse that. So we can convert the pH back into the hydronium ion concentration, or the POH back into the hydroxide ion concentration. And here's the mathematics of that. Okay. So the hydronium ion is really 10 raised to the power of negative pH. Hydroxide is really 10 to the power of the negative POH. So your calculators have different keystrokes. I don't know which one that you'll be using. So let's just do this. Calculate the hydronium ion concentration given the pH. So what you're doing is really going 10 to the negative pH, right? And that would give you that value right there. So by the way, when you do 10 to the x, that's really the anti-log, isn't it? So where you find this 10 to the x button is normally right above your log button. Got a bunch of calculators in here. I love being dyslexic. I can't find anything, but anyway, all I know is that of all the calculators I looked at, they're almost always that way. So here I compared 8.777 and 7.777. Those are a difference of 1 pH unit. And look at the difference in the concentration. Just to remind you that 1 pH unit is a factor of 10 in terms of the concentration of the ions we're talking about. 2 difference units in pH represents a 100-fold difference. So here, calculate the hydroxide ion concentration if the POH is 7.77. So again, it's simply 10 to the negative POH. I put in the value, and there's the number. So that's this practice with your calculator. Anybody have any questions on that? So back to water again. Here's the reaction that we looked at. So we got the conjugate acid, the conjugate base. We talked about all that. Why can we not also do the equilibrium constant for water? It's simply going to be products over reactants. But then I have water crossed out because it's a pure liquid. So KEQ, we can call KW, because this is for water, is equal to the hydronium ion concentration times the hydroxide ion concentration. But furthermore, we can calculate what this is supposed to be. In pure water, both of these are 10 to the minus 7. This gives us, this times this is equal to 1 times 10 to the minus 14th. So we can boil that down to this relationship right there. Okay. And this is good for a couple of different things. If I know the hydroxide ion concentration, that's a constant. I can calculate hydronium ion and vice versa. Okay. Also, I need to understand this. If I have solution of water and I add acid, hydronium ion concentration goes up. What has to happen to the hydroxide ion concentration? It has to go down. And now, because I have more hydronium than I do hydroxide, it's going to be an acidic solution, and the pH will go down. So similarly, if I add base, the base increases and the hydronium ion has to go down. So calculate the hydronium ion concentration of a solution given the hydroxide ion concentration. So all I'm doing is taking this relationship right here, inputting the hydroxide and solving for hydronium ion concentration. So here I did that math. Here's the concentration of hydronium ion. Then I can get the pH of that by simply taking the negative log of it. Okay. So again, in a red box, because this is a mathematical manipulation, I don't really care if you understand it or not, it doesn't really matter. But I'm going to take KW right here and put it into a different form, different mathematical format using logs. So I have this, and I'm going to inverse both sides of this equation. So this is 1 over hydronium times 1 over hydroxide, and 10 to the minus 14th. The inverse is 10 to the plus 14th. So then I'm going to take the logarithm of it. Now it's a property of logarithms. If you take the log of a multiplication formula, multiplication turns into addition. And also division would turn into subtraction. So here's what I get mathematically. And the log of 10 to the 14th would simply be 14. But now if you look at this, this is really a definition of pH. This is the definition of POH. So what I have now, this mathematical formula simply came from this KW right there. But here, if I have pH, I can always calculate the POH because they both have to add up to be equal to 14. So now we have every single corner of what my students and I called the square of death one time. So if I have the hydronium ion concentration, I can turn that into pH using that equation. If I have the pH, I can turn it back into hydronium ion using the inverse of that. If I have pH, I can convert that into POH using our new form of that equation. If I have the POH, I could turn that back into OH using the antilog. If I have the OH, I can turn that back into hydronium ion using simply KW. So I asked my students one time, hey, let's call this the square of death, and they really liked that idea. And I said, well, that's kind of negative, so we could call it the square of life, but yeah, they weren't into it. So what that means, if I give you one of these 4 things, you can solve the missing 3. Before the final exam, I will give you all these equations and stuff like that, but you just need to be able to do it on your calculator. So I can't waste your time doing this, but here I get 1, 2, 3, 4 things. I'm giving you the one of the 4 things. You should be able to solve for the other 3. Same thing here, same thing here. Okay. So you just have to sit there with your calculator and make sure that you know how to do those calculations. So, any questions so far? So, this chapter can be quite mathematically challenging, but to tell you the truth, I've done a pretty good job of breaking it up into portions and then telling you what you need to know and what you don't need to know. So this section here, calculating the pH of strong acids and bases in water. So the key to everything is figuring out how you're going to solve the problem. So for example, in physics, you hit a baseball and then they have you draw the trajectory. So you see all the forces that are acting on that baseball. But in chemistry, we don't draw pictures. We don't have a cognitive map to help figure things out. But what I'm trying to get students to do is take the equation and use that as the cognitive map. So calculate the pH of a 0.01 molar solution of HCl. I almost guarantee you that if you took that to a graduate student in chemistry or some tutor, they really wouldn't know what to do. But if you write the equation out, you're going to see, oh, HCl, that's a strong acid. That's a one-directional arrow. That means I start off with 0.01 HCl and none of that. But as soon as it touches water, that's completely gone. And stoichiometry tells me one of these gives me one of those, so 0.01 gives me 0.01. Every time I make one of these, I make one of those. And really, what is it I need to get the pH? Simply that. That's all I need. So the negative log of 10 to the minus 2 is simply 2. Calculate the pH of a 1 molar solution of HCl. Okay, so I do that and I get 10 to the 0. 1 times 10 to the 0. Oh, wait a minute. That's 1, right? 10 to the 0 is equal to 1. The log of 1 is 0. So does that mean that the pH can be 0? Well, yes, it can. Calculate the pH of a 12 molar solution of HCl. So this is concentrated hydrochloric acid. It's a fuming acid. If you open up the top of the container, which I don't want to go get it right now, I don't want to smell acid fumes, but if I did have it here, I'd open up the container and you would see it just fuming like this. As it goes into the vapor phase, reacts with water and condenses the water, and you simply don't want to breathe that because that's, hydrochloric acid. So to make concentrated hydrochloric acid, they take hydrogen chloride gas and they pump it into water, cold water, until it becomes concentrated. And it can get up to 12 moles per liter. So what is the pH of that? The negative log of 12 is negative 1.08. It's like, oh my God, the pH can be negative. Sure it can. It simply means the negative log of something. So, what about for a 0.01 molar solution of magnesium hydroxide? So what I need to do is draw the cognitive map. Here's magnesium hydroxide. I get 1 magnesium and I get 2 hydroxides. So if it completely dissolves, and it would because that's a dilute solution, That 0.01 is going to give me 0.01 of this. It's going to give me 0.02 of that because that's the stoichiometry. So look, 0.01 molar eighths of magnesium hydroxide. For 1 mole of magnesium hydroxide, I get 2 moles of hydroxide. That's how I get that, simply stoichiometry. So here is the hydroxide ion concentration. The POH would be that. Here I figured out the pH and then hydronium ion. So I decided not to put this on the exam. So that means that you're not going to have to use stoichiometry to do what we just did. But let's just look at this. Calculate the pH and the Ka for an acid if, in a 1 molar solution of the acid, there's 0.811 moles per liter of the acid. And I know that sounds really bizarre. What it means is that you started to make a 1 molar solution of this acid. You calculated how much you needed to add into what volume to get 1 molar solution. Mix it up. But then someone came along and they measured, well, how much acid is there really in the form of HX? And the answer is 0.811. So what happened to this missing 0.189 moles per liter? Well, it went that way. So one of these would give me one of these. 0.189 would give me 0.189. I make 0.189 of this, I make 0.189 of that. It's all stoichiometry. So what is it that I need to get the pH? I got it right there already. The negative log of 0.189 is 0.7. What do I need to get the equilibrium constant for this? Oh, okay. So the equilibrium constant would be products over reactants. And each of the products is 0.189, right? That's why that's squared right there. And equilibrium, the amount of the acid left over is 0.811. So I crunch all these numbers and I get 0.044. So what does that number mean, 0.044? That number tells us that there's 44 parts of products for every 1,000 parts of reactant. So did the reaction go far? The answer is no. Look, the number is right here. This number tells us this information up here. At equilibrium, most of it is still in the unionized form of the acid. So is this a strong acid? No. How would we quantitate how strong it is? Well, we could calculate the percent ionization. We got 0.189 moles that are ionized out of every 1 mole per liter that we put in there. So this acid is about 18.9% ionized, 18.9% dissociated. So here's the pH of a solution of a weak acid. What is the Ka and the pKa? Oh, wait a minute. That means you can make a solution of an acid, measure the pH, and you can calculate all these different things. The answer is yes. So here's the reaction. That's our cognitive map. So what is the concentration of the hydronium ion? It's given to us by the pH. So 10 to the negative pH is that number. Okay. So now I got 1.7 times 10 to the minus fifth moles per liter of this. What do you think this one is? It's the same, isn't it? Then, if I start off with 1 mole per liter of this, and I lose 1.7 times 10 to the minus fifth, I have that many moles per liter left over at equilibrium. So, the Ka simply products over reactants, but now I have numbers for these things, so there's the Ka. And the pKa is simply the negative log of that number. So anyway, I want you to see that these calculations can be done. If you take Chemistry 161, 162, that 1 year series, you'll have to do this stuff. But it's in the red box, so I'm not going to put it on the exam. So any questions so far? So when there's no questions, it's really easy to get through the material real quickly. Okay. So if you remember from chapter 12, we were writing chemical reactions in 3 different ways. We were writing the traditional, the total ionic, and the net ionic ways. And so we'll do that for some neutralization reactions. Okay. So here we're taking sulfuric acid, completely neutralizing it with sodium hydroxide. So that would be an aqueous solution, that would be an aqueous solution, that's a liquid, that's an aqueous solution. But when I write the total ionic equation, I write it the way it would actually appear in solution. So this would be completely ionized. Because it's a strong acid and because we're taking it off anyway because of this. So that completely dissolves. Water is simply what it is. This completely dissolves because sodium ions or sodium containing molecules are mostly soluble. And then with the net ionic equation, I throw away, take out all the spectator ions. So what did hydrogen do? Oh, it reacted with this to form water. What did sulfate do? Nothing, it's a spectator ion. Sodium, spectator ion. Hydroxide did something. So the net ionic equation is simply the formation of water. So again, this emphasizes what the driving force is for a neutralization reaction. Hydrogen ions, reactive. Hydroxide ions, reactive. Water, stable. So here's a couple of other further points. Don't ionize a weak acid or a base. Simply leave it as a molecule because that's the predominant form that you find in solution. So here's a weak acid, here's a strong base. So the total ionic equation would be, I leave it this way, even though there are some that is ionized. That would be dissolved, that's simply water, that would be dissolved, right? And the net ionic equation, the only spectator I can leave out is sodium. So what that shows us is that a weak acid doesn't give all of its H plus to the weak base water. But would it give it to the strong base hydroxide? Yes, it would. Okay. Anyway, so these just illustrate some more things. And then titrations. So we did titrations in chapter 17. So for the sake of completion, we'll do it here as well. This is where it's almost always or always done, is in the chapter on acids and bases. But then again, titrations are not only acid-base reactions. All they are is using stoichiometry in a chemical reaction. So let's just do one. A student titrated 100 milliliters of a malic acid solution with 85 milliliters of a 0.2 molar hydroxide solution. So give the concentration of the malic acid solution. So we have to write the balanced reaction, and then we have enough to calculate either the moles of the acid or the moles of the base. So let's figure out what we have. Here's 100 milliliters of the acid, but we don't have the concentration, so we cannot get moles of the acid. Here is the volume of the base and the moles per volume of the base. We have everything we need to calculate the moles of sodium hydroxide. So we do that. So we calculate that there's 1.7 times 10 to the minus 2 moles of hydroxide. So then I have this, and I have to use stoichiometry to get into that concentration. So I got that many moles of the hydroxide, 2 moles of hydroxide for every 1 mole of malic acid, and here is the moles of malic acid. That malic acid is in 100 milliliters. So that is enough now to calculate the concentration. All you need is the moles and the volume, right? So I gave another one. We could do that. So a student titrated 50 milliliters of a malic acid solution with 35 milliliters of 0.2 molar aluminum hydroxide solution. Give the concentrations in both moles per liter and equivalents per liter. So first we need to balance the reaction. And then what do we have enough of, the acid or the base? Here's the volume of the acid, we don't have the concentration. Here's the volume of the base, we got the concentration. So we can calculate the moles of aluminum hydroxide. So we did that. So here's the moles of aluminum hydroxide. Then we used stoichiometry to convert moles of aluminum hydroxide into moles of malic acid. Notice that there's a 3 in front of that and a 2 in front of that. So now we have the moles of malic acid, and we know its volume. It's in 50 milliliters. So here's the calculation. Here's the moles, here's the liter. So here's our moles per liter. And then if we need to get equivalents per liter, we see that for malic acid, there's 2 equivalents of H plus in every 1 mole. So that converts moles into equivalents. Now we have equivalents per liter. So we can see that it's twice the amount of moles per liter. So I think back when I was taking general chemistry, I was traumatized by it, and teaching was not very good. Books were not very good. What really saved me is that one of my friends from high school at Kalani High School was a graduate student in chemistry. And I hadn't seen him for several years. And I'm walking around Bilger Hall, and there he is. Hey, how's it? And anyway, he showed me a couple of things. And when I learned that if he can do it, I can do it, I never had any problem with chemistry anymore. I just knew that I could do it. But I also remember the way they taught stoichiometry is you have to memorize this equation. And I was not good at memorizing, and it was just ridiculous. So I don't use it. What we did to solve these problems right here with stoichiometry, we went back and we used basic principles. We used the conversion factors that you learned. There's not very many of them, right? Not very many tools. But what they wanted me to do was just memorize this equation. So I'm going to show you the equation. It's equivalence per liter times equivalence of liter times liter for the base. What this does is gives you the concentration of H plus, and this gives you the concentration of the OH minus, because that's what you're going to have at neutralization. They're put into the solution at equal amounts. But how could I get this right here? Well, I could take the equivalence of hydrogen ion per liter, that's the normality, times liter, or the equivalence of base per liter, which is the normality of the base, times a liter. So what it means is you memorize this equation, you get one equation you can solve for only one unknown. So in the problem up above, what were we solving for? The constant, or the equivalence per liter for the acid. So rearrange the equation, plug in the numbers, and there's my answer. So now, if I was spending my whole day doing titrations, yeah, that would be a useful equation to use. But if I'm doing the occasional stoichiometry problem, I'm simply going to use stoichiometry. Yeah. So I don't know if you guys like these jokes or not. If you don't have to read them. This one, when I read this one, I was just cracking up. I just couldn't help it. And then, yeah, I got to bring back some Chuck Norris jokes. He's still alive. He's probably 80 by now. But yeah, pretty funny. Okay, so that really completes chapter 19. Chapter 20 and 21 are actually short chapters. This was a long chapter. So it took us an hour and a half, 2.5, about 2 hours and 40 minutes to get through lecturing on chapter 19. So we have about 20-something minutes. I'm going to ask you if you have any questions about anything. Anybody? No questions. So what I'll do is I'll just start reviewing a little bit. So in chapter 19, here's some properties of acids and bases. Here's the definitions. And in this chapter, at this type of chemistry, the major definition we use is the Bronsted-Lowry definition. Okay. Although we see that for hydroxides, we have to use more or less the Arrhenius definition, even though it's not the preferential way to do it. We just end up having to do it because of this. And if you ever take organic chemistry, then you'll be using the Lewis definition because that's all reaction mechanisms. So one of the most important things you need to be able to do is write the reaction for an acid and water. Okay. And so how do you do that? You write the equation. The acid is the acid, water has to be the base. And so by definition, hydrogen goes from the acid to the base, and then you just write what you have after that. And then that's so important because this whole thing here gives us the equilibrium constant, products over reactants, but then gives us the pKa. And this hydronium ion gives us the pH, and the pH relates the whole thing to the square of depth. So that's how everything is related. And it all starts off by being able to write the equation for an acid and water. When it comes to polyprotic acids, unless you're putting it in with a strong base, which is called a neutralization or a titration, only one acidic hydrogen comes off in water. Okay? And it may not come off all the way. And with polyprotic acids, you got the situation like this. Is this an acid or is it a base? I'll have to tell you which one that you'll use for that particular problem. So here's some psychology about why do acids ionize. And how did I do that psychology? I use all the stuff we learned from Unit 3. Okay. Difference in electronegativity, polar bonds, nonpolar bonds. And what do we know? Nonpolar bonds are stable, they're not reactive. Polar bonds can be reactive. So naming acids, you need to know these two systems, right? Those two ways of doing it. Naming bases, there's only one, so you have to know how to do that, but you have to also know what ammonia is and what methylamine is, for example, in amine. And then we learned about equilibrium constants. So most of the time we use a homogeneous equilibrium, and when we do that, we leave out pure liquids and solids. We only care about what's in the solution where the reaction is taking place. That's all we care about. So the equilibrium constant, here we leave out water, even though it's part of the reaction. And bases are treated the same way. It's simply products over reactants. And then, if we're given numerical values for all the different concentrations, we can crunch the numbers and get the equilibrium constant. So a large equilibrium constant means that the reaction gives a lot of products. And then we learned how to take the negative log of something. So textbooks concentrate on pH. Everything is pH, 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 pH. And then they treat all these other things, they kind of sneak them in. And I'm just trying to focus on the process. What does P stand for? It's the negative log of something. So I first showed you the negative log of the Ka, or the KEQ. And later on we did pH and pOH. Let's see. So then we talked about strong acids and weak acids. So I was explaining to you that all we need to know, and this is for my class, other people might do it quite differently. There's only 7 common strong acids. There are other ones out there that are not common. You're not going to find them in the lab. All of these could easily be in the lab. For myself, I have nitric acid, sulfuric acid, hydrochloric, perchloric. I don't know if I have these anymore. So these are the strong acids. If it's not an acid from this list, then you treat it like it's a weak acid. So a double directional arrow, it does not go all the way to completion. So here's some calculations based upon percent ionization and whether it's a strong acid or weak acid. Again, strong acids will be 100% ionized. And of course, it's never going to be completely 100% ionized, but you know, then we're going to get into uncertainty and significant figures and all that stuff. Then another huge simplification is that strong bases simply have hydroxide in the formula. Weak bases don't. And the weak bases are going to be ammonia and the analogs of ammonia. Okay. So here is ammonia. You make water act as an acid. In other words, you're hydrolyzing water, which is redundant. Hydrolysis is simply hydrolyzing water. And of course, H plus goes from the acid to the base. So here's your conjugate acid and your conjugate base. And then the amines act in the similar way because, look, they still have that NH2, which is what causes water to be hydrolyzed. And we have to think of water as both a weak acid and a weak base at the same time. That's why I came up with this little thing over here. So here's conjugate acids and bases. This is what we started with today's lecture. So all we're saying is that we already knew what is the acid and what is the base, but now we're looking at the product side and saying, well, if it's reversible, one of these has to be the acid, one of these has to be the base. And again, you're just following where the H plus goes. Let's see, so there's equilibrium constant. So this little section on here, I guess I could label as KSP, but anyway, I don't want you to think that KSP is something different than KEQ or anything else. No matter what you're doing, if it's a capital K, it's an equilibrium constant, and you do the same thing every time. Product concentrations over reactant concentrations. Leave out pure liquids and solids. And the strengths of conjugate acids and bases. So this is a little bit tricky. To tell you the truth, I rewrote this right here, I don't know, 4 times, trying to figure out what is the best way to do it. And so, just to summarize, if you have a strong acid, it really wants to get rid of its H+, its conjugate base is going to be weak because it doesn't want to take that H+ back. If you got a strong base, it really wants to take that H+ from something. And once it gets it, it's not going to give it away. So its conjugate acid is going to be weak. But most things fall into the moderate. Okay? So if you're a moderately strong acid, it's like, well, I kind of want to get rid of my H+. But once you got rid of it, you know, okay, I might take it back. So there's the equilibrium there. Same thing with over here with bases. And then if you got a really weak acid, it doesn't really want to give away its hydrogen very much. But once you do give it away, it's like, hey, I want that back again. It becomes a strong conjugate base. Okay. And hydrolysis of water by salts. So notice that this right here is hydrolysis, even though I didn't put it in that section, because it's something that I put into water that doesn't have hydroxide, but end up forming hydroxide. That hydroxide was formed from water. Same thing here, okay? You can call that hydrolysis as well. So the reason why this is important, because that helps us explain why the ocean is not acidic, it's alkaline. They say the ocean, the early ocean, was very acidic because of all the carbon dioxide around. And then we had volcanic activity to produce SO2 and SO3, which ends up giving the sulfate in the ocean. So a couple million years of that helps the pH of the ocean go up a little bit. And then plants take CO2 and turn it into oxygen. So you remove the CO2 from the air, so therefore removing it from the oceans, and the pH was able to go up even higher. Of course, then the problem was the Earth was too dumb. It created so much oxygen that humans were able to evolve. And what are we doing? Putting the CO2 right back and making the oceans acidic again. We dig it up out of the ground and put it back into the air. So here's the ionization of water. Okay. And anyway, so water is hydrolyzing water, but at extremely low amounts, right? 10 to the minus 7th is 1/10 of a billionth of a mole in a liter. And then we did a bunch of calculations, okay, to get the square of death. Okay. So that's one thing that you need to know how to do, is do all the mathematics for the square of death. And here, just calculating the pH. So if you take a strong acid and put it in water, or you put a strong base in water, because you're assuming it is 100% ionized, 100% dissolved. So for every molecule of strong acid you put in there, you make a molecule of hydronium ion. Same thing for hydroxides. Okay. And can we do this simply using stoichiometry? Yes, we can. I won't put it on the exam, but I feel like it should be, but I won't. And then just revisiting the 3 ways to write chemical reactions. And then revisiting titrations. Let's see. And then revisiting the best jokes ever, right? Okay, well, we finished chapter 19 and then we reviewed it. Before we have our final exam, we'll give a review on all of everything. That probably will be on May 11th. Okay. So that means that 21, 20. Okay. So on May 1st, I'll do a review of Unit 4. So make sure you have questions for that day, okay? Unless you know everything already. So any questions on anything? Okay. Well, I'm going to end the meeting then, unless anybody has any questions. Oh, let's see. Finally, I see from text message that there are people out there listening. Okay, well, anyway, you guys have a great day. And if you have any further questions, just send me an email or ask on La Lima in discussion and messages. Okay, take care. Aloha.